Everything that has ever existed in the universe has been built with atoms, most of which were chemically bonded to other atoms, of course. But considering that all atoms are made of just a few subatomic particles, and bonding can generally be thought of as just a sharing of a pair of electrons, that's an incredible amount of diversity to come from just a few subatomic particles and a simple sharing of valence electrons. How do we explain that metals conduct electricity while plastics don't? Why are some materials brittle while others seem to be impossible to break? How do we explain all of this diversity when in all cases atoms are still bonded to one another by a sharing of electrons? What we need to understand this are models of structure. All right, to help us understand the diversity of materials in our universe, we are going to draw on a concept that we've touched on already in this class, and that's called electronegativity. As you'll recall, electronegativity is really a measure of greediness toward electrons. So for example, if we are considering a bond between two hypothetical atoms, atom X and atom Y, the degree to which each of these atoms are electronegative determines how much they're able to draw the two electrons that are in the bond between them toward itself. So for example, if X is significantly more electronegative than Y, most of the electrons in this bond are going to be drawn toward the X atom, and we'll have one end of this bond predominantly negative and the other end predominantly positive. We call this a polar situation, or a polar bond, if the electronegativities of these two atoms are significantly different. But of course, the opposite could also be true. If X and Y were, say, the same atom, or atoms with very similar electronegativities, we would expect the two electrons in this bond to be shared equally. Now this would be a nonpolar bond in this particular case, often referred to as covalent in most cases. And we can actually attach numbers to this, since all elements have a number associated with their electronegativity. And so the difference in electronegativity between these atoms can often be calculated. And if that difference is small, say between 0 and a half, then we can characterize this bond as being nonpolar. If the difference is a little larger than that, so say between a half and say 1.9 or just under 2, then we can characterize this bond as a polar bond. Again, remembering that most of the electron density will be spending its time on the atom that is the more electronegative of the two. Now this phrase polar comes from the notion that this bond would essentially at that point have two poles, a negative side and a positive side. If most of the electrons in this bond are drawn towards this end, then this would be the negative side of that bond, and consequently this would be the positive side. We often indicate this with some special notation. It's a delta symbol with the sign of the charge next to it. So a polar bond can be indicated as such. Now there is another case where the change in electronegativity can be even more extreme. And in these cases, we don't actually refer to the bond as polar or not. We instead refer to this as an ionic bond. Ionic coming from the fact that in cases of this extreme disparity in electronegativity, we assume that essentially all of the electrons in the bond are spending their time with the most electronegative atom. These atoms have a difference of electronegativity that is so large that one atom essentially steals all of the electrons from the other, resulting in a negatively charged species and a positively charged species, and therefore ionic becomes an appropriate word for those. All right, so how are we going to use this information in a way that's fruitful to teach us about materials in the world? This is called a Van Arkel-Ketelaar triangle, And it's maybe a lot simpler than it looks. Really, all we're doing here is we're asking ourselves some simple questions about neighboring atoms. Notice on the bottom here, we're talking about average electronegativity. And then I'll draw your attention over here to the left-hand axis where we're keeping track of the change in electronegativity. So just like I finished talking about, if our change in electronegativity is large, we've got ionic type bonds. If our change in electronegativity, however, is very, very small, most often we've got a nonpolar covalent type of bond. But let's also consider the average electronegativity of the two atoms in the bond. For example, I'll bring back my X and my Y. What if these two elements have roughly the same electronegativity, but neither of them are particularly electronegative anyway? Well, that would put them down here, in which case both elements or both atoms are very non-electronegative and are similarly non-electronegative. That is where we place a class of materials called metallic elements or metallic bonds. However, if they are fairly strongly electronegative, say a couple of fluorine atoms, if they are two fluorine atoms, their difference in electronegativity will be 0 because they're both the same element, but they have a high electronegativity, so they're both greedy, but they're both equally greedy. In that case, they'll be forced to share equivalently. Thinking of bonding in these two dimensions is a convenient way for us to imagine how electrons are shared between pairs of atoms. They can be shared equally amongst elements that aren't really very greedy for electrons anyway, or shared equally amongst elements that are very greedy toward electrons. Or they can have a significant disparity in their electronegativities, and one element takes the majority of the electrons from the other. So what are the implications of this? If I know where my particular bond lies in this diagram, how do I use this information to make sense of the materials that I can interact with on a day-to-day basis? Well, let's start with metallic substances. The model of structure for metals is that of a large series of nuclei surrounded by what are thought of as a mobile sea of electrons. In other words, all of my nuclei can be arranged one after the other into what looks like a seemingly infinite arrangement of atoms, but between all of those atoms, I've got the electrons that are being shared in that bonding environment, but with no real strong tie to any particular nucleus. This is why we refer to them as a mobile sea of electrons. In other words, the electrons that are binding these nuclei together are free to move throughout the entire structure. And this is entirely consistent with this notion from the Van Arkel-Ketelaar triangle that tells us that metallic bonding occurs in scenarios where my elements aren't differently greedy. In fact, they're not greedy at all. In other words, the electrons are more or less just donated to the greater good, so to speak. So the electrons in each element, at least the bonding electrons in each element, are put into the interstitial regions between all of the elements and are allowed to be mobile. So what are the implications of this? The implications of this are that these materials, built from metals, should be able to conduct electricity very effectively. And why not? The electrons aren't particularly bound to any localized place within this substance, and instead they're able to mobilize throughout the entire substance. This sounds exactly like a wire, doesn't it? Electrons should be able to transport themselves through this material in an almost effortless fashion. So metallic bonding substances we expect to conduct electricity quite readily. These substances can also be quite malleable. In other words, we can bend and shape them as we choose. And again, this model of their structure is consistent with that, because as I strike this piece of material with, say, a hammer, I can move the elements in such a way that they simply reorient themselves, but the sea of electrons that are holding all of those nuclei together are able to accommodate any different arrangement of those nuclei. So shifting them, if you will, becomes entirely possible and doesn't damage the structure, and certainly doesn't change the electronic nature of the bonding in this species. Therefore, metals tend to be quite malleable. I can bend them into the shape that I want them to. But what about ionic substances? So as I increase the difference between the electronegativities of these two elements, making one much more electronegative than the other, what should I expect to happen in terms of its macroscopic properties? Well, ionic species, as the name implies, are those that essentially donate their electrons entirely from one end to the other. Sodium chloride is a typical example. When we have sodium chloride, we expect that the difference in electronegativities here is so great that sodium essentially donates its electron entirely to the chlorine, and what we really have is a positively charged sodium atom next to a negatively charged chlorine atom. And why wouldn't we have that? Opposites tend to attract, right? So the positively charged sodium ions would very much like to spend time next to the negatively charged chloride ions. And in a seemingly infinite network, recall that a solid, something that you can see with your eyes, would be consistent of billions and billions of atoms. So what that would mean is that I would have a seemingly infinite network of neighboring sodium chloride, sodium chloride, sodium chloride, on and on and on, in a structure that looks like this. These ions will orient themselves next to one another in all three dimensions and will be held together simply by the coulombic forces associated with their different charges. So positives like spending time next to negatives, so on and so forth. But that comes with a consequence. If I were to strike this substance and cause atoms to move even just slightly, it becomes possible to put two equal charges next to one another. In other words, I can line up my positives and my negatives, and this is an unfavorable thing. They will be forced to repel. And of course, they will do that. And this is what gives substances like these, like salts and other ionic materials, their brittle characteristics. It doesn't take much to knock the elements out of alignment, and not only are they then not favorably aligned, but they're actually repulsive, and these substances fall apart quite readily. Think of table salt, for example. We don't necessarily think of that as being an extremely robust, sturdy substance. A block of salt is actually a very brittle thing. Likewise, if we wanted to compare and contrast it to something like metals, we wouldn't expect this structure to be particularly good at conducting electricity. This is why we don't make salt wires, for example, because the electrons are relatively localized to, in this case, the chloride ions. And all ionic species will have a negative component to them. That's why they're ionic. And that negative component is particularly greedy for electrons. So there's no driving force for these electrons to be mobile and travel throughout this substance. So I certainly wouldn't expect properties of electrical conductivity from an ionic species. And likewise, if I wanted to think about maybe melting a species like this, that would probably also not be very easy to do because of the fact that these ionic species, again, like to be next to one another. And taking a solid and melting it into a liquid requires enough energy to break the connections between those neighboring atoms. And there isn't a lot of driving force for that in particular in this particular case. So I would expect ionic substances to be relatively high melting point substances that are quite brittle and don't conduct electricity very well. And this is indeed true, and it all boils down to the notion of bonding. Now, what about covalent and polar covalent substances? If I've got elements that share electrons equally, but who are both greedy for those electrons. Well, substances that fall into this category are known as covalent network solids. And a great example of one of those is diamond. We've all heard of diamonds. Maybe you didn't know that diamond was pure carbon, but it is. And we already know that carbon likes to have 4 electron domains in its vicinity. And if you think about it, you can come up with a beautifully symmetric structure by interlocking a seemingly infinite network of carbon atoms together, all in their tetrahedral arrangement. This is an incredibly strong structure. In fact, diamond is one of the hardest substances known, and the reason should be obvious. Each of these carbon elements are covalently bonded to one another, and there is an awful lot of force required to break one of these covalent bonds. A covalent bond is a very strong bond between neighboring elements. Likewise, each of these atoms is relatively electron greedy, but of course they are all equally electron greedy. So diamond is not a particularly good electrical conductor. Again, there's no reason for electricity to want to pass through this structure because each and every one of these elements is relatively greedy for electrons in this particular form. Now, carbon comes in many different forms. These are called allotropes. One allotrope of carbon is diamond, but another allotrope of carbon is graphite. Graphite is comparatively much weaker than carbon because graphite is composed of these two-dimensional planar sheets of carbon atoms all in an sp2 state. Right? So trigonal planar state, which allows them to orient themselves in these planar networks. And when we stack planar networks on top of one another, we get these sheets of graphite, which are strong, but not quite as strong as diamond. So these covalent network solids are an entirely different bonding structure, again due to arguments around electronegativity. Elements that are particularly greedy for electrons, but equally greedy for electrons, make for a very strong and sturdy substance, especially one that I don't expect at all to conduct electricity. Likewise, because of the strength of the connections between all of these atoms, these substances tend to have very, very high melting points. It isn't very easy at all to take a substance like this and melt it into a liquid form, as you would probably imagine, given that diamond is the prototypical example here. So is that sufficient to constitute an explanation for all of the matter that we're familiar with? Of course, the answer is no. What about the air that you're breathing right now? That doesn't necessarily fall into any of these different classifications, which brings me to the fourth and final classification of substances, or fourth and final model of structure in our universe, and that is molecular substances. Molecular substances require a lot more discussion, and in fact, that will constitute most of the remaining parts of this course. Thinking of covalent network solids and ionic solids and metallic substances is definitely interesting, and there's lots of variety there in terms of different types of structures and different types of species that we've observed in the world around us. But they pale in comparison to the diversity afforded to us by molecular substances. What's the difference? Well, essentially, the difference here is that in the first three, covalent network solids, ionic solids, and metallic substances, we considered atoms bonded to their neighbors. Now, of course, that's also true in molecules. For example, let's think about the water molecule. But what we're primarily interested in when we are discussing a substance is a bulk amount of these particular species. So what I'm really thinking about when I think about a glass of water is, of course, billions and billions of water molecules swimming around in each other's presence. So The difference here is that when I think about the structure of a billion water molecules, I'm interested in the interactions between the two. Just like for covalent network solids, ionic solids, and metallic substances, I was interested in the interaction between neighboring atoms. Because in each of those examples, metallic substances, ionic substances, and covalent network solids, they were comprised of a seemingly infinite network of atoms. Molecular substances are different fundamentally because these will be comprised of a seemingly infinite network of molecules. And so we have two levels of diversity here to consider. Of course, we can build a seemingly infinite number of molecules, and then we can have a seemingly infinite number of those molecules together in a substance. So before I can talk about the properties of a molecular substance, I need to learn about how different molecular species interact with one another. And that's the focus of next class.